Hello guys, welcome to another video. In this video, we are going to discuss about different types of probability distributions. So, as you know, in the previous videos, we have already discussed about like how to do different kind of probability distributions, how to identify what is a probability distribution, the conditions required for them. And in this lecture, as I have already told in the previous one, we are going to discuss about binomial distribution, Poisson distribution, and stuff. So in each of these distributions, the necessary thing that needs to be done is to find out all of their properties regarding their PMF, their expectation, their variance, their standard deviation, and finally how to find probabilities using them, right? So I'll just give a basic review of what we have done before. So done before. So we already know what is a random variable. Right. We also know what is the properties of a random variable, and we know what is a probability distribution. Now, using these two things, we can actually make sure that we understand the binomial distribution completely, which is our first distribution which we are going to learn. So, this distributions I'm talking about, these are special kind of distributions which occur more frequent than others, and they can be used to solve a bunch of different class of problems. So, I'll give the heading here. Probability distributions. And we are going to start off with the one I have been talking about, binomial distribution. So, what is a binomial distribution? First of all, a binomial means two terms, right? So, as we have learned, monomial means one term, binomial means twice, trinomial is a expression containing three terms, and polynomial is like three or more or two or more. So, a binomial distribution is a probabilistic distribution where two events are involved, obviously. So, it's a binary event, okay? So, a distribution where two events are involved as outcomes. So, a binary distribution or a binomial distribution is a distribution where your outcome is generally based upon a success or a failure. Okay, so there are like two types of distributions. So, generally, the outcomes are failure or success. Okay, so I'll give a example now. When we write it as like this, a random variable x following binomial distribution can be written like this: x follows bin for binomial, and there are two parameters n and p for a binomial distribution. So we will know what the parameters are. So let me write down the parameters for a binomial distribution. Parameters are n, which is the number of trials, and p, which is the probability of success. Okay, right. Okay, so The first thing we need to understand is how to actually visualize this. So consider a coin tossing example again. So suppose you have a coin and you want to toss it, like, let's say 3 times. Okay, so suppose we toss a coin 3 times. So for a binomial distribution, you need to understand these key points. Each trial must be independent of the others, right? So each trial must be independent, that is not dependent upon the previous trials. So here you can see, as we toss a coin, obviously each of the coin tosses are independent of the other, and the result does not depend on what the previous result was, right? Also, probability of success shall remain constant. So each trial must be independent and probability of success must be constant. So if these two conditions are satisfied and it's a discrete distribution, that is distribution involving a finite number of trials and stuff, it can be modeled as a binomial distribution. So in the coin tossing example, we can see that n is equals to 3, and probability of success, if we call the random variable x as number of heads, or we can call the success as getting a heads, then the probability of that is half, since there are 3 coin tosses, which are basically called here as trials, and getting a head has probability 1/2 always, right? Because the coin actually does not change to an unfair coin in the middle, so it always remains a fair coin, and that is why the probability of success is 1/2 regardless, right? So it can be modeled as a binomial distribution. Now, what is the PMF? For a random variable x following binomial n comma p, the PMF, or the probability mass function, remember, as I have already modeled like before, that probability of x equals to 0 is something, x equals to 1 is something, and like that. Here x has the values in binomial distribution, x carries all the values from 0 to n. Okay, so naturally the probability distribution should assign a probability to each of these n plus 1 values, right? And it does so, and it gives us the probability in this format for any k. For probability of x equals to k, where k is any k from 0 to n, the probability is modeled as nck, where nck is the binomial coefficient, p to the power k into 1 minus p whole to the power n minus k, and this goes on for all k equals to 0, 1, 2, and so on up to n, right? So this is our probability distribution for a binomial distribution. This is what we call the PMF. Okay, now we need to check if it's a probability distribution. This is a common exercise. So firstly, obviously all the terms are positive, that is nck is greater than 0, and p to the power k into 1 minus p whole to the power n minus k is also greater than equal to 0, since 0 less than equals to p less than equals to 1. Therefore, probability of x equals to k is greater than equal to 0. So the non-negativity condition is satisfied. Now we need to show that the sum of all probabilities is 1, if you remember. So therefore, sum of all probabilities would be just summing this probability from 0 to n, probability of x equals to k. This is the sum of all probabilities, which is basically k equals to 0 to n nck p to the power k into 1 minus p whole to the power n minus k. But this is just the formula for the binomial expansion, right? Because this would just give you p plus 1 minus p whole to the power n. If you do not really understand how the binomial distribution corresponds to the binomial formula here, this is the expansion of the formula. I will just write a note below which will explain you why this is so. It is 1 to the power n, which is 1, and this can be derived from the following formula. This will be taught in the lessons of algebra, but the proof is not really needed in this section. For x belongs to real numbers, 1 plus x whole to the power n is given as k equals to 0 whole to the power k equals to 0 to n nck x to the power k. And for ab belongs to real numbers, so I'll give you both the formats, and n belongs to a natural number, a plus b whole to the power n. This expansion can be written as k equals to 0 to n nck a to the power n minus k into b to the power k, right? So using this formula, you can see that here a is 1 minus p and b is p, which means a plus b whole to the power n, this thing equals, which gives you a 1, right? Okay, so that gives us a basic idea of binomial distribution. Now we shall try to find the probability distribution for the case of like 2 and 3. Okay, so case tossing 2 coins. As you know, we have done all of these examples before, but now we are going to do it with the binomial distribution, and you will see how easy it becomes once I define what expectation and variance of this distributions are. So when you get this kind of problems, you can easily see why you can model it as a binomial distribution and use the results directly. So tossing 2 coins, right? Then the random variable x follows a binomial distribution with trials 2 and probability 1 by 2, right? So what will be the PMF? The PMF can be modeled easily. X equals to 0 should be 2c0 into 1 by 2 whole to the power 0 into 1 by 2 whole to the power 2 minus 0, which basically gives you 1 by 2 square, or which is 1 by 4, right? As expected, because that's what we have got previously as well. Similarly, probability of x equals to 1 should give you 2c1, and same thing, half to the power 1 into half to the power 2 minus 1. This should give you 2 divided by the same thing, which is 2 square here, or in other words 1 by 2. And lastly, probability of x equals to 2 should give you 2c2 into half to the power 2 into half to the power 2 minus 2, which is same as 1 by 4. And all of these probabilities add up to 1. So in general, when you find it, you can write that x equals to k would give you 2ck into half to the power k into half to the power 2 minus k. If you see, these two things can be added because they have the same base, and the exponents can add up, so it will become 2ck half to the power k plus 2 minus k. So the k's cancel off and it becomes 2ck by 2 square, or in other words 2ck by 4. This is the expression for any k, and you can simply put k equals to 0, k equals to 1 and k equals to 2 to find all the 3 probabilities, right? Similarly, if I take the case for tossing 3 coins, then we can say that x follows the binomial distribution with parameter 3 and probability 1 by 2, and the PMF is 3ck into 1 by 2 whole to the power k into 1 by 2 whole to the power 3 minus k, right? For 0 less than equals to k less than equals to 3. So if you simplify this part, it becomes 3ck remains in the numerator, and in the denominator you have 2 cube, which is basically 3ck divided by 8. Now an important question arises that obviously we can define these distributions, but what about the expectation and the variance, right? So previously when I told you how to find the expectation, I told you that the general formula for finding the expectation was E of x equals to summation, where you take a random element y in the sample space A and you multiply y with the probability of y and you add all of them, right? In case of binomial distribution, what would it be? So let's take a general one. So a general distribution would be like this: given x follows binomial of n comma p, find the expected value of x. So how do we do this? Let's give the solution to this, and this would work for all other cases as well. In binomial distribution, this would be a standard formula for you to use whenever you can model a problem as a binomial distribution. You can use this formula directly. You just have to mention that this formula and the statement, and then you can use it. I do not think any proof is required whatsoever until and unless it is mentioned. So firstly, we need to find the PMF because the probabilities are required in order to find the expectation. So firstly, the PMF is probability of x equals to k. See, the PMF is basically a way of defining all the probabilities associated in a single pattern, right? So if they can be found in a single way, you can just write it down in the pattern, or if they cannot be, then you have to write it down individually, but in both cases you need to define the PMF. So here we have a formula, so we are just writing probability of x equals to k equals to nck into p to the power k into 1 minus p whole to the power n minus k. Okay, now comes the expectation part, and I am going to prove it to you as well. Then the expectation is E of x equals to summation. Now you do not need to actually take random elements from the sample space because we know the sample space. It's basically k belongs to 0 to n, right? That's the values the random variable takes. So we can sum it from 0 to n. Since it's discrete, we are summing. If it was a continuous variable, we would have it integrated from 0 to n. But so we sum it, and we are finding the expectation, right? So we can do k into probability of x equals to k. That's the expectation, right? So the value multiplied by its probability. Now obviously we can ignore the 0 part, but let's just keep it for the moment, because this would give you k into nck p to the power k into 1 minus p whole to the power n minus k, right? 0 less than equals to k less than equals to n. Now note, in order to solve this, we need to find a few things. Firstly, we are going to simplify this part, k into nck. So obviously nck is n factorial by k factorial into n minus k factorial, okay? And k factorial, and now I'm going to adjust a few things. So there is a k here in the numerator, and k factorial can be written as k into k minus 1 factorial, and this is n minus k factorial. So this k is cut off and we get n factorial by k minus 1 factorial into n minus k factorial, right? Now this can also be written as n into n minus 1 factorial into k minus 1 factorial into n minus k factorial. And if you notice carefully, this part is basically n into n minus 1 c k minus 1, right? Using this, putting this back, we get expectation of x is summation of k equals to 0 to n. This part has been transformed to this part, so we can write n into n minus 1 c k minus 1 p to the power k into 1 minus p whole to the power n minus k. Okay, now the first is k equals to 0, so the first term is n minus 1 c minus 1. Now since minus 1 has no value, so this series looks something like this: n minus 1 c minus 1, and whenever you have a minus 1 in the denominator of a binomial distribution, of a binomial coefficient, it is 0 essentially. So this part is 0, and we start from the first part, which is this n minus 1 c 1 minus 1, and we go all the way up to with obviously the probabilities p to the power 1 1 minus p whole to the power n minus 1, and we go all the way up to n minus 1 c n minus 1 p to the power n into 1 minus p whole to the power 0. Okay, so this would give us in summation form k equals to 0 to n minus 1, actually n into n minus 1 c k p to the power k into 1 minus p whole to the power n minus k. Okay, right? Okay, so this serves the purpose, but we need to have another way of doing this, because we just need to find out what's going to happen here once we finish this, because this p here is an extra term, right, in order for the formula. So once you take out this p, this becomes an exact binomial formula, which is this. And this becomes 1 minus p whole to the power, this n minus k can be written like this, right? So this becomes a binomial expansion now, which is basically 1, because that would evaluate to p plus 1 minus p whole to the power n minus 1, which would give you 1, and which would give you the expectation as np, which means the expectation for the binomial distribution is just the product of the number of trials and the probability of success. Therefore, expected value of a binomial distribution is E of x equals to np, right? And in this way, for the tossing of coins case, so case 2 coins, you can see that x follows binomial of 2 comma half, so the expected value should be 2 into 1 by 2, which is 1. Similarly, for 3 coins, you know that x follows binomial of 3 comma half, so expected value should be 3 into 1 by 2 or 3 by 2, which is 1.5, right? So that completes our lesson for the binomial distribution for this day. In the next video, we shall continue looking at the variance and the standard deviation and then related problems of binomial distribution, the different problems that can arise from this kind of distributions. So that ends our lecture today, and do be sure to check out the Britus Math app, the link of which is given in the description. It's a complete mathematical app and statistical tool where you can find all your related calculators for statistics and probability, and the notes regarding this video lessons are also included in it. Thank you so much. We'll see you in the next video.